All right. Well, hello, chemists. Okay, seems that we have people joining. All right, which is always good to know. All right, now I hope I do not hack your name. All right. Well, Kevin. Okay, hold on. People joining. All right. Is always good to know. All right, now I hope I do not hack your name. Kevin. Ding, ding, ding. Right. I should not get an echo now because we are live streaming this one to YouTube. Okay, so all right, let's get back in here then. All right, so anyway, welcome then, chemist, to the second week, the second episode, if you would, of the masterclass in A-level chemistry. And all I do on this one is quite simple. I go through any difficult questions, any difficult concepts that you want me to go through during the week. All right. So if you want to, by all means, email me during the week, then email me my email address. I'll put it here. Okay. And so this one here. All right. So this is if you have a question, you say, hey, can you cover this one like next time? All right, this one is me. All right, it's G Matthews because I'm Graeme at EmpowerMind. That's my company name. .co.uk. Hello, Samina. So anyway, here we are then. So on this one then, yes, by all means, if you want to say, hey, next week, can you cover this? By all means, put it into this email address there and they'll get that done for you. Okay, so I just opened the chat window, and so if you're online on Zoom, okay, then by all means, do me a favor, just pop something into the chat if you want to. Let me know they're actually here. But what I wanted to do is today, I wanted to go over back titrations. Okay, so this is how I do it, chemist. Now, I actually do these live. All right, meaning that I do have my calculator here. All right, calculator here. This is actually done live, so it's not reading off notes when I do these. Okay, so back titrations. Now, back titrations are they're guaranteed of being on the next end of unit test, the next mock exam. However, we're doing this in the COVID-19 pandemic is that they are fair game. All right. Now, having said that, chemists, they are a little complicated to get set up. All right. But if you follow along with this diagram, they're actually not that bad. And the reason that I go over them with my students is that then you end up gaining those points that other students just didn't know what to do with. They didn't understand the concept. So it's really easy. Look, at the start, okay, what you have is you have a flask. They always say there's a conical flask, and they give you a starting amount of acid or base. And we'll do 3 problems today. If we've got time, we'll do three problems a day, okay? So you're going to obviously know, you know the concentration is moles over volume over 1,000. All right, so change pen codes here. All right, got so many little windows open here. All right, this one, I'm assuming that we know. Concentration is moles over volume of 1,000. And so from this then, from the starting concentration, you got concentration given, moles you need to calculate, and then volume is given. So from this, what you can get is that you can get the starting amount of acid or base. Now, in the middle, all right, in the middle, what they say is that they say, right, there is some kind of a reaction taking place. And they normally, add the metal. I think we do the one today with like magnesium carbonate. They're going to add something that's also going to react with the acid. All right, or the add thing that's going to react with the base. But this is in excess, as in you have more of it than you can possibly use up. So in your conical flask, then, what you've got is you've got this. All right, right there. Here's your magnesium carbonate reacting away. All right, quality of language. It's always like this, but normally you and I would call it bubbles away, bubbles of gas is seen. What they like to see is they like to see the word effervescence, because effervescence just means to bubble. That's a fancy way of saying it, to give it bubbles, right? But you add magnesium carbonate to this, and you have some acid or base, whichever one they're using, left over. Now, you think, all right, that sounded pretty good, Graeme, got to admit, but how are we supposed to figure out how much acid or base is left over? Well, at the end, this is how I explain it. Imagine, if you would, that you had a rectangle like this. You know what they say, a picture's worth 1,000 words, or just loads and loads of time me just like, explaining this. Look, this is my rectangle, and the entire rectangle is the starting amount of acid, right, or alkali. 9 times out of 10, it's an acid. So this entire thing is the starting amount of the acid, for example. Now, the bottom bit of it, this is the amount of acid that reacted. Okay, and you normally see it as they give you the equation, like, magnesium carbonate and HCl. All right, this bit up the top here, right? This is the amount of unreacted acid. And he's saying, how do you get this bit? This is the bit that you get from the back titration. So this is right here. This is your back titration. And the dead giveaway is it's always going to be something like HCl and sodium hydroxide. They always give you a second equation. HCl and sodium hydroxide is going to give you sodium chloride and water, right? Now then, hopefully this has clarified what we're doing, because it's the same thing over and over again. It doesn't matter what the question is that they ask you. It's always the same thing. They always give you the starting amount of acid. Then they say some reaction takes place. And then they say there was a back titration at the end, or the excess acid was neutralized with so many mLs of sodium hydroxide. Now, after that you've done this, after you found out the amount of acid that actually reacted, well, then you can take this data and you can answer the question. So it's like you need to get all of this done, like in a starting amount of acid, ending amount of acid that you've got with the back titration. All of this to figure out the amount of acid that actually reacted. And so you can answer the question. For example, they'll say to you, how many grams of like the magnesium carbonate was present, or what was the purity of the magnesium carbonate, or what was the percent composition. And you're thinking, oh, after this, the bit in green just becomes really, really easy, right? So here we go then, chemists. Hopefully my ink is going to stick today. All right, let's see, looks good so far. All right, so, oh, I spoke a bit too soon, I think. Just let me hit sync right here to make sure. Now, I see we've got Samina with us. Samina, hello. All right then. So if you're thinking, if you want access to these notes, you want access to my resources, okay, just send me an email and I'll add you to the share bit for my notebook. All right. In other words, you know, I can share my notebook with you, and then you can have access to all of these notes here. Okay. So here we go then. On this bit right here, we sync one last time, and that ink should indeed disappear eventually. It normally does. All right, then it says right here, limestone is mainly calcium carbonate. Student wants to find out what percentage of limestone was calcium carbonate. All right. It says a 1 gram sample of limestone is allowed to react with 100 cubic centimeters of 0.2 molar HCl. The excess acid required 24.8 cubic centimeters, 0.1 molar sodium hydroxide. Any back titration. Calculate the percentage of calcium carbonate in the limestone. Now, I know you're thinking, oh dear, well, this looks like an awfully difficult problem. You know, there's like loads and loads of data floating around. I've got volume, I've got concentration, I've got moles. Where exactly do I start? Simple. Go back to the diagram right here. Very first thing that we're going to do is that we're going to figure out how much acid I had at the beginning. So you see a sort of start right here. It's the very first thing that I'm going to do. So here we are then. All right. So in black right here, change my ink color to black. All right, so at the start, yes, we need to calculate the moles of, and let's get the acid right, the moles of HCl. So you're thinking on this bit then. Here's my rectangle, put my rectangle right here. Here's my rectangle like this. Very first thing we need to do is that we need to figure out how many moles of HCl we have at the beginning. So the entire bit in blue, this is the starting amount of HCl. All right then, so as I said, I'm doing this live. So concentration is moles over volume over 1,000. All right. And so my pen right here, I got moles is concentration times a volume over 1,000. Well, let's see. Now, the concentration that they gave you was ding, 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 0.2 molar, right? So you've got 0.2 molar right here. So moles is 0.2, right? Moles, yeah, per decimeter cubed. And hold on, can I get better looking 3 there for the cubed, right? Times, now the volume of the acid at the beginning. So where's my highlight? Oh, I'm going to move this down a little bit. All right, in yellow, I've got 100 cubic centimeters of 0.2 molar HCl. All right then, boom, right. So you've got 0.2 molar decimeter cubed, and it was 100 cubic centimeters, right? Now, you know that you got to divide by 1,000, all right, to move from cubic centimeters to decimeters cubed, right? So anyway, with my calculator, let's make sure I got this one right. So turn on trusty calculator here. Now, I always do these live, meaning that, you know, I'm not reading off a script or some notes of actually problems I've done before. It's kind of like, no, let's do these live. All right. So I got, when I did this, now, so mean if I got this wrong, oh, please let me know. All right, I got 0.02, which is what, 2 times 10 to the minus 2, all right, moles, like this. Okay, so here we are, 100 cubic centimeters, 0.2 molar HCl. All right, 100 cubic centimeters, 0.2 molar. And let me highlight this one in yellow. I'll keep everything color coordinated, like so. All right, then. And so we can keep track of things at the end, right? HCl. Now, you're saying, right? So this is the starting amount right there. This is the starting amount of HCl. Now, it does undergo some kind of a reaction. So over here in this bit, I'll put the box on this bit. Look, this is where it undergoes some kind of a reaction here. The calcium carbonate is going to react with the HCl, okay? Now, problem is we don't know how much calcium carbonate we have because it's an impure sample. But we're thinking over here then, if I put that here, this is the mystery bit right here. This is the amount of HCl that reacted with the calcium carbonate, right? Now, what we do know is that there was an excess amount of HCl, which means up here in the top portion of my rectangle, this is the amount of HCl that is left over. So to get this bit, we say, well, I'm now going to titrate this. Can I spell titrate? I hope so. Try it again. Right. I'm going to titrate this with some sort of hydroxide. It's the dead giveaway. If you're ever wondering, well, how does the pieces fit together? They always tend to titrate whatever's left over with the sodium hydroxide, which is this bit over here, right? Now, I'll color coordinate this bit in highlighter. Oh, let's do pink. Thanks to Microsoft, we'll do pink, right? So this is the bit there that when I put it down in the bottom, we'll make it pink. All right then, so I'm down to here. Now, next bit then is complete, or a better way of phrasing it is saying determine the moles of acid left over after the reaction. Right. So underline this, make it look nice and neat. Okay. Right then. Well, I'm going to take my HCl and sodium hydroxide right there. So I'm going to say, right, the HCl left over and the sodium hydroxide that they titrated it with, you know, like a standard titration you probably did, like one of the very first experiments that you did, very first practicals. All right, sodium chloride and H2O. Now, I always do this. I always write down concentration, moles, volume, like this. I always write down concentration, moles, volume. Just keep things nice and organized, if you would. All right, then. So let's see. In pink, keep everything organized. That's Graeme. Keep everything organized. Make this pink as well. It says the excess acid required 24.8 cubic centimeters of 0.10 molar sodium hydroxide. So this bit here. All right, 24.8 of 0.1 molar. Come down here. 0.1 molar sodium hydroxide. Come down here and look. 24.8 cubic centimeters of a 0.1 molar, moles per decimeter cubed, solution of sodium hydroxide. Now, what I've got to do then is figure out the moles of sodium hydroxide I actually have. Right, well, like we said, concentration is moles over volume over 1,000. And so therefore moles would be concentration times volume over 1,000. All right, so let's see, it's 0.1, that's my concentration, 0.1, times 24.8 cubic centimeters divided by 1,000. So this is in decimeters cubed. And let's see, now this one on my calculator should be out to -3, just eyeballing it, I think. So hold on, clear that. So I've got 24.8. All right, times 0.1. Let's see, divide this by 1,000. And it is indeed. My math is correct on this Sunday afternoon. Yay. Look, 2.48 times 10 to the -3. All right, moles of sodium hydroxide. Now, 1, 2, 3. Got to make sure, let me highlight this so everything is color coordinated for you, right? So, you know, highlighted the equation, and here we are here. So this is now highlighted, we can all see what's going on. Right then, so this bit is, well, 2.48 times 10 to the -3. So up here then, you're thinking, right. So we know the starting amount, right? The starting amount of HCl was what, 2 times 10 to the -2. All right, so this was down here, 2 times 10 to the -2 moles, like so. And so the entire rectangle is worth 2 times 10 to the -2 moles. We know that the amount of HCl that was left is what, 2.43, 2.48. Hold on, 2.48 times 10 to the -3. And so all we've got to do is figure out what this bit is down here. Right, here we are then. So the amount of acid that reacted, in this case, the magnesium carbonate, the missing bit, right? This bit right here, the missing bit, is, well, let's see. It must be the moles of HCl at the start. Has to be the amount of the moles of HCl reacted, which is what we're trying to find out, plus the moles of HCl that was left over. Okay, so, well, okay, logic, right? I mean, the HCl that you started with Part of it reacted, part of it's left over. You're thinking, okay, whoops, hold on, is my ink going to sink? I don't know. Hold on a second there, chemists. All right. Don't know if my ink wants to sink or not, but here we go. All right then, so it will eventually sink, but look. So the amount of HCl that reacted then has to be the moles of HCl at the start minus the moles of HCl left over, which is, now at the start, was it not, is what, 2 times 10 to the minus 2, right? So I had what, hold on, pen. 2 times 10 to the minus 2 minus, well, the moles that reacted, that was left over, 2.48 times 10 to minus 3 minus 2.48 times 10 to the minus 3, okay, means that the moles of HCl that reacted, in this case with the magnesium carbonate, well, let's see, do this live, hold on. So I've got 2 to the minus 2, all right, minus what, 2.48 to the minus 3. Okay, I've got 0.1752 moles of HCl. Yeah, so I've got 2 to the minus 2, and I subtract from that 2.5 to the minus 3. This is the amount of HCl that reacted. Okay, so having said that, let's color code this bit in. Oh, we'll do light blue. Thanks to Microsoft, we'll do light blue. Oh yes, my pane, my page just synced there. Oh, good, good, good. Right, good. My ink sticking. I was thinking about it. All right then. So anyway, chemists, here we are then. Look. So now, after all of that, now we can answer the actual question. All right, because recall I said on this bit, I said, ding, 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 ding. Oh, the ink didn't stick on this bit. I said at the end, you do all this stuff, and then you can answer the actual question. Well, let's take a look then. So the actual question was on this bit. Calculate the percentage of calcium carbonate in the limestone. All right, so it's this bit in yellow right here, highlighted in yellow. There's a mean like this. Look, take a look. All right, now on this one, chemist, do you notice how they've been a little bit tricky? Meaning that they've got a 1-to-2 ratio here. Yeah, a 1-to-2 ratio. So you've got to watch out for that. It's not always going to be a 1-to-1. Probably going to be like a 1-to-2. But anyway, here we go. Obviously, I'm going to write down to here. Okay, I've got my calcium carbonate. I was going to copy the equation down. Calcium carbonate and 2HCl, all right, gives you calcium chloride and H2O, right? So it is this one right there. All I've done, you see the equation right there. I just copied it down. Calcium carbonate, 2HCl, and I better put in my carbon dioxide right now. Again, so I'm going to write down here, answer the question at last. So I'm saying on this bit, right here. Concentration, moles, volume. Now, this is the tricky bit, right? Because you're going to come in, it's standard for me to write down concentration, moles, volume. It doesn't matter if I'm, using all the variables or not. I say automatically write it down. But over here, I had what, 0.1752. So my moles of HCl is 0.1752 moles of HCl. So I can erase this bit. It's kind of like a knee-jerk reaction. As soon as I see titration, I write down concentration moles volume. But it's a 1-to-2 ratio. I'll do it this way. It's a 1-to-2 ratio. And so therefore, I need to get the moles of calcium carbonate. All right, so moles of calcium carbonate. Well, that's going to be 0.1752 moles of HCl, and there's a 1-to-2 ratio. So you put moles of calcium carbonate up the top, because it's what we want, and down the bottom is 2 moles of HCl. 2 moles of HCl. Right. Now then, okay. So basically you just divide it by 2. That was a fancy way of saying divide by 2. And so I get moles of calcium carbonate is 0.00876. Now, chemists, what you got to do is this, look. You've got to help the examiner out, or in the COVID-19 pandemic, you've got to help your teacher out. Label everything with units and what you're talking about. Because what they're not going to do is spend hours looking for numbers on the page. Help them out right there. So this is moles of calcium carbonate, right? Now then, you're thinking, okay, well, put a vertical line here. I need to go from moles of calcium carbonate to grams of calcium carbonate. And so the MR of calcium carbonate. So hold on then. Let's see. Well, calcium is 40. Right, calcium is 40 and carbon's 12. And it got 3 times 16. Right. For the oxygens, so what 3 times 16 is what, 48, and 12 and 40 come back in as 100 grams per mole. So again, look, I always just write down the units and I cross out going left to right. You know, students ask me about this one. It's like, well, I did math. I say math, not maths. I did math 38 years ago, a very long time ago. And so I just write everything down, cross it out, go from left to right. I don't do the thing with the triangles and everything else because it just gets me confused. Right, so this one here then, it's going to be 10. All right, 0.876 grams of calcium carbonate in my sample, right? Now, having said that, the sample, if I go back to the actual question up here, is only a 1 gram sample. So if I come down to here then, because it's only a 1 gram sample, all right, so I have to move down here. All right, so this one, typical, right, percent purity is going to be, what, 0.876 grams of calcium carbonate. They want this by mass, of course, over a 1 gram sample. Yeah, this is 87.6%, like this. Hold on, I draw percent better than that, probably. Hold on. Right, waiting for ink to catch up. Let's see. There we are. Right, percent. Now then, that is like your real typical question with a back titration. So if you have a question, you know, by all means, put it into the chat. Now, look, we're streaming this one through Zoom. Okay, so if you're on the YouTube, watching the YouTube one, well, then we're streaming this one through Zoom. So if you're in Zoom, you can put a question into chat. All right, but hopefully that clarified that one for you. So this is, you know, your standard back titration. So we went over the overview. Yes, all about, you know, the starting amount, the end amount, the back titration. We did one that was involving acids. All right. And let's do one more. I think we've got time just for one more. So this one, okay. I chose this one because it's one with the base. So you're thinking on the exam, whichever format it's in, well, they may give you the one which is in an acid, or on the other hand, they may give you the one that's in a base just to get you confused. But you know what? It's the same exact thing. All right. So here we are then. I'm going to highlight this, and I think we started out in yellow. All right. And so the very first thing that we've got to do is I've got 100 cubic centimeters of aqueous sodium hydroxide. All right. So on this one, just like we did in the previous one, and I'll skip all the way down the end. All right. Because basically we'll just work the problem and then fill the answers in at the end. Look, you need, in this one, you're going to get the starting amount of the base of the sodium hydroxide. Okay. Now, normally they add it to acid. In this case, they're adding it to base. Okay. So you're thinking, all right, starting amount of sodium hydroxide. So here's my rectangle over here. The very first thing we need to do then is, well, I would say draw a slightly better rectangle, but that's just me. All right, try it again. No, not too bad. Right, is look, we need to get the starting amount of the sodium hydroxide. Okay, so on this one, back to black, you've got concentration is moles over volume over 1,000, right? Hopefully, if you're following along with the concept of the rectangle and with the 3 conical flasks, the very first thing I need to do then is I need to get the starting amount of sodium hydroxide, which is concentration times volume over 1,000. All right. Let's say concentration was 0.5 and 100 cubic centimeters. So that's easy, right then. So, all right. Pending it down here. Hold on. 0.5, 0, right? Moles per decimeter cubed times 100 over 1,000. Okay. Let's say I got 0.05 on this one. Okay, moles of sodium hydroxide. All right, so anyway, let me make sure my math is indeed correct. All right, because it would be embarrassing if it wasn't. Okay. Yeah, I got 0.05 moles of sodium hydroxide. Math still works on a Sunday afternoon here. Lovely. So again, look, put a box around it. And this is the one that I'm going to keep in the yellow highlighter like this. No. I haven't said that, is it? Right. Okay. This is at the start. The number of moles of sodium hydroxide we just said is 0.05, right? Now, having said that, they then allow it to react. Now, in this case, chemists, what we've got here is, it says all the ammonium sulfate reacted to all the ammonium sulfate reacted. By the way, I'm going to put a 1 to 2 here, okay? And all the ammonia have been driven off as a gas. Yes. The unreacted sodium hydroxide, okay, required what 27.3 cubic centimeters of 0.6 molar HCl. So up down here, all right, I'm just going to, hold on, I've got to keep my pen colors coordinated here. I'm just going to say this. Right, calculate the moles of sodium hydroxide left over. So I'm going for this bit right here. Well, again, underline this may look nice and neat first off. Hold on. So I got right there, I got concentration is moles of a volume over 1,000. I mean, I think you would admit, chemists, that once you've done one of these, you've done them all. And really, it's just figuring out what to do with each piece of the data, right? And so what I say is this. Draw the rectangle first, yeah, and then solve the moles of sodium hydroxide at the start, number one. Then number two, solve for, I'll change pen colors, the moles of sodium hydroxide left over. And then number three, calculate the moles of sodium hydroxide used. In other words, what I don't do is I don't go from like left to right in the question and I solve it using the way that they've given me the data. I always use the same exact thing, like, you know, step one, step two, step three, right? Now, having said that, hit sync. Got to keep everything synced here as much as possible. All right, so the moles of sodium hydroxide left over then coming from the titration. And so this one is your standard. If you always wonder about which of the two equations do you want to use for the back titration, it's always going to be, the back titration is always a simple one. It's always either sodium hydroxide and HCl or HCl and sodium hydroxide. All right, it's always a nice, easy equation to use. All right. It doesn't have anything at all to do with the reacting mass at the beginning, like magnesium carbonate, or in this case, ammonium sulfate, right? So here we are then, moles of sodium hydroxide left over. Well, hold on, concentration times volume over 1,000. And so they said, wasn't it 0.6? It was somewhat weird. It was a 0.6. All right, I believe it was 0.6. Ding, 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 ding. Yeah, 0.6 mole per decimeter cubed and what, 27.3. Right. All right. Moles per decimeter cubed, and it was what, 27.3 cubic centimeters, which we got divided by 1,000. All right, so here we go then. This one, take a look, hold on. So I go, well, 0.6 times 27.3 divided by 1,000. I'm getting 0.01638 moles of sodium hydroxide left over. Now, again, chemists, did you notice how what I did is units, what I'm talking about, and so the examiner has a really good idea of following along with what you're writing. All right, so I'm going to color code this one, and I believe, yeah, this one was pink. All right, Microsoft pink, you know. All right. And they come down to here. I'm going to put this one in pink as well, so that you can follow along. All right, hopefully a bit better, wherever you're watching this. All right then. Now, all we're going to do then is last bit is step 3. So this is what 0.0163 moles of sodium hydroxide left over. Well, we need to just, before we do step 3, we need to figure out hold on, 0.01638. Got to put this into my little triangle, my little diagram here. So this was 0.01638. It's like to keep things, you know, nice and organized here so we can see what's going on. And I'll put the box back in now. All right. But anyway, when I've done the calculation, I put the piece of data up there. And so then, you know, it's easy to figure out what's going on. Okay, now we just need to figure out the moles of sodium hydroxide used. So come down to here. Last bit then is calculate moles of sodium hydroxide used. All right, well, from the equation previously, we said, on the previous example, we said this, look, the moles of, in this case, sodium hydroxide at the start must be the moles of sodium hydroxide used in the reaction and the moles of sodium hydroxide left over, which we got from the titration, right? All right, then here we are. So if I need to figure out the moles of sodium hydroxide used, it's just going to be the moles of sodium hydroxide at the start, which we calculated in step 1, and subtract from that the moles of sodium hydroxide left over, which we got from the back titration. And so at the start, wasn't it 0.05, right? Yeah, so this was 0.05. And this one we just did, this was what, 0.01638, right? 0.01638. Okay, so calculated time, right, 0.05 minus 0.01638. I got 0.03362 moles of sodium hydroxide used. Now, what they want to know, hold on, I've got to hit my sync button here. All right, what they wanted to know then on this one is, the very last question, they wanted to know the moles and mass of ammonium sulfate. But we all come all the way up to here. Did we notice how it's a 1 to 2 ratio between the moles of sodium hydroxide and the moles of ammonium sulfate, right? So we come down to here. I'm going to say from the equation, right, 1 mole of ammonium sulfate reacts with 2 moles of sodium hydroxide. So all you got to do then is this again, like we did in the previous example, divide by 2. So on this one, chemists going to do this. I like saying this. This is my tripwire. Because you got to start to think like a teacher, right? You go, what's the one thing that they could add on to it to make it a bit more tricky? And the answer is that it's always going to be like 1 to 2. It's like never anything easy. Normally it's like 1 to 2, right? So, okay. But if you notice that, great. So I got 0.03362 moles of sodium hydroxide, yes, and I've just got to divide it by 2. Now, again, do you notice that what I do here is I always write everything down for the examiner, for your teacher, and so you're thinking they can follow along. Because I'm not saying that you would, but let's say you got the final answer wrong. Well, then you're thinking you can get the working out points, right? Whereas on the other hand, if you didn't do a nice, easy working out example for them to follow along with, it's going to be a bit more difficult for them to look for the points and give you back the points, right? So here we are then. I got this bit. So basically divide by 2. And so this ends up with, hold on, pen, right here, I got 0.01681 moles of ammonium sulfate. Yeah. Now you're thinking, right? Because this was in the actual question, and we'll fill the question in now. So then when you look at it later, we'll see how everything comes in together. So this is the moles of ammonium sulfate. Now, they then needed the mass. Right, so the mass of ammonium sulfate. Now again, you got to stop and think, why did they pick ammonium sulfate? Well, because getting the MR is actually a little bit tricky because you've got the 2 down there, right? So you're thinking, yeah. So what you've got is you've got 2 nitrogens, right? You've got to bring the 2 in. So you got 2 times, what, 14 for nitrogen and 8 times 1 for the hydrogen. Oxygen is what? Is it 32.1 and 4 times 16? Right. There's a pair of table open, so I just did that from memory. So it's right. All right, then. So let's see now. 2 times 14 is 28, and 8 and 32.1 and 64. We're coming back with, I got 132.1 grams per mole. And so therefore, Microsoft's going to sync just one last time here. All right, it will sync eventually. Look. All right. Actually, you know what? I should call this the MR. Yeah, you just synced. MR of this is that, and so therefore I can get the mass. The mass of ammonium sulfate then is 0.01681, all right, moles up here in green. Let me highlight this in green, right? Like so. And let's say times 132.1 grams per mole. And so just multiply this by, hold on, 0.01681, like so. I end up with, well, let's say 1.01681. I got 2.22 grams. Now we're going to have to check the significant figures now of ammonium sulfate, right? So, having said that, let's put some numbers in up here onto this. Okay, so the original number of moles of sodium hydroxide in 100 cubic centimeters, well, we said that was 0.05. Right, so this bit is 0.05 moles, like so. So this is obviously this is the starting amount, right? This is your starting moles of sodium hydroxide. What they're doing in this question, Samina, is that they're walking you through it because, you know, maybe you didn't learn how to do the rectangle thing. The number of moles of HCl, this is your back titration. Like so. And so the back titration one that we got, that was what, 0.01638. This was 0.01638 moles, like this. Let's see. The number of moles of unreacted sodium hydroxide, all right, neutralized by the hydrochloric acid. Well, yeah, this one, they're getting at, you know, sodium hydroxide and HCl goes to sodium chloride and water. So basically it's a 1-to-1 ratio. And so it's going to be 0.01638 moles of sodium hydroxide. Now, let's see, it said, use the answer in part A and calculate the number of moles of sodium hydroxide which reacted with the ammonium sulfate. And so this bit here, then, this bit would be what we call step 2. Step 2 on our diagram. Okay, because they want to know the moles of sodium hydroxide which reacted with the ammonium sulfate. If we come down to here, right. Ding, ding, ding. It was 0.03362, right? This was 0.03362. What they're getting at is that, hint, you need to divide by 2, right? Like the 1-to-2 ratio that we had going. All right, now the moles of ammonium sulfate, all at the end. Right, now this one, I think this one was like an 8-mark question, something like this. But look, here we are right there. The moles of ammonium sulfate is, going down here, 0.01681. Right, was it 0.01681? And then the mass of ammonium sulfate then was what, 2.22. Right, so I had what, 2.22 grams, like this. Now, they didn't worry too much about significant figures here, but if you see this, look, I got 3 sig figs here, I got 3 over here. All right, everywhere you look at is just 3 sig figs. Now, the reason why I mention this is because if they get a bit funny with the points and the mark scheme, sometimes they take off points for not having the right amount of significant figures. Anyway, that was it. So this then, basically this then, chemists, this was a little overview on back titrations, right? So I hope you found it useful, hope you found it helpful. Right, now, you got my email. My email up here is right there. I can move this out the way. Right, gmatthews@empowermind.co.uk. So if there's anything that you want me to cover next week, next Sunday, same time, Sunday at noon, then by all means, just shoot me an email. Let me know what you want me to cover. If not, I'll find another challenging set of questions to do. All right, then. So on this bit, let's call it a wrap. Samina, thank you again for showing up. You have a good day, and I will see you next Sunday at noon. So have a great week.